if you have a polynomial, it's not so hard to evaluate it, right? So suppose you have the function x cubed minus 5x plus 1, and somebody asks you to find out what f of 0.1 is. Of course, you can just plug in and find the value, no problem, right? Yeah. So, yeah, I wouldn't even calculate. But it's a whole different story if you are asked to find sine of 0.1 without a calculator. This one you can do it without a calculator if you have the time. You just patiently write out the numbers, multiply them, and get the value. But this is very different, right? You wouldn't know how to calculate sine of 0.1. What's the real difference? Why is it that this you can calculate whereas this you can't?
Because sine is a trig function.
Sine is a trig function and you don't know where to plug in, right? Whereas for polynomials, this is made of what kind of operations?
Plus,
Multiplication, subtraction, addition. You can even have rational functions, polynomial over polynomial, you can still do it. So, in other words, as long as your function is just made up of these four operations, addition, subtraction, multiplication, division, you can calculate it. Whereas sine, you can't. That immediately throws a question like, how did the ancient people before, like all these calculators, know how to calculate, for example, sine of 10 degrees? Can you imagine how someone would know the value of sine of 10 degrees?
Eyeball it.
Hmm?
Eyeball it.
Yeah, I mean, eyeball it by what? You
The unicircle.
Okay, so unicircle would be one way, but you would probably draw a very accurate degree 10 right triangle, right? Yeah. And make it really large so that you can be as accurate you can, and then calculate the ratio of opposite over hypotenuse, right? So then you can get approximate values. And you can actually get the entire trig table by drawing these values. Yeah. Okay. But still, the limitation is that you can't figure out what sine of, say, 0.1 is, because the best you can do is just approximate. That's all you can do, right? Yeah. All right. So here's an idea, and some bold individual started thinking, well, maybe sine is a polynomial. Some polynomial like this one. Right? And this was not even a single person. Many people thought about this. And in fact, they succeeded somewhat. Among those people are MacLaurin and Taylor. Those are the famous people because they used calculus. But I searched up Wikipedia, and it says even before them, there was some Indian mathematician who was able to figure that out. But okay, well, so if sine x happens to be a polynomial, then we are good because we can actually calculate it, right? However, there's a very fatal flaw to this plan because if you draw the graph of sine, it's like that, right? How many zeros does a quadratic equation have? Quadratic equation has how many solutions?
As many as power.
That's in general. I said
Oh, wait,
quadratic.
It's just two. It's just
Two. Quadratic means power of 2. A cubic equation would have 3, right? So in general, a degree n polynomial has how many zeros at most? N. Yeah. So look at the sine graph. What's wrong with this if you say this is a polynomial?
Goes to infinity.
It has how many zeros?
Is that infinite?
Infinite zeros. So immediately you see that sine x cannot be a polynomial. But some people never quit. They still insist, okay, well, whatever. We'll just make it, what kind of polynomial? Infinite polynomial. Just make it infinite polynomial. Maybe that's going to work. It has infinitely many zeros, so make it infinite polynomial. And that's why I wrote it like this. Usually you write a polynomial in descending degree order, so the highest order comes here. But then if you have an infinite polynomial, that's impossible. You have to start this way. And because you quickly run out of numbers to put, instead of writing it this way, we're going to write it as like a0, a1x, a2x squared, and so on and so on. And sigma notation, let me just write one more. In sigma notation, how does one term look like? It's always x to some power with a. That's always true. So what should I put here and here? N. With n starting from?
1.
No, you start from 0.
Oh,
Because when n is 0, what's x to the 0th power?
1.
1. Anything to the 0th power is 1. So indeed, when n is plugged in as 0, it will create the very first one. And then it's an infinite series, so it goes to infinity. And such a series is called power series because it's a series, infinite series with powers of x. Okay, so so far so good, but this would be useless unless you actually knew what the value of a0, a1, a2, a3 are, right? How would you find these values? The idea is that this equal sign is an equality between what?
Sine x.
It's an equality between functions. So it's not a conditional equation. What's a conditional equation? Like x squared equals to 2x. That's a conditional equation, right? When is this true? When x is 0 or 2, right? Yeah. Or else it's not true, right? On the other hand, this is an equality between functions. X plus 1 squared equals to x squared plus 2x plus 1. In this case, this is true for all values of x, right? Now, if two sides are equal for all values of x, if they're equal as functions, there's a nice trick that we can use to figure out what a0 is. What should we do? Any ideas? How can you find a0 if we know that the two sides should be equal for all values of x? Yes?
Set x to 0.
Yes, you plug in x equals to 0. And then you get sine of 0 equals to a0, and then plus every one of these will be just 0 because it has zeros to some power, right? Now what's sine of 0? 0. Sine of 0. Graph of sine is like that, right? So sine of 0 is 0. Remember? You should remember the graph. So you get a0 equal to 0. Okay, next. Now we immediately run out of good numbers to plug in because anything you plug in, say if you plug in 1, then all of these will be there and you get an equation which cannot be solved because you have infinitely many unknowns. So that's no good. But then there's another thing we can do, which is that if two sides are equal as functions, then differentiating both sides should still give you equality between functions. So if you differentiate sine, you get cosine of x. If you differentiate a0, you get 0. What do you get if you differentiate a1x?
1.
X differentiates to 1, but that's a constant multiple, right? So it's
A1,
a1 times 1. So it's just a1. What about this one? a2x squared?
A2 to
2a2 x, right? X to the first power. And then 3 comes down. You have 3
3a3
x squared. So on and so on. So if you differentiate both sides, if the equality is equality between functions, the derivatives are still equal. Now let me just demonstrate it here. This is a conditional equation, right? What do you get if you differentiate both sides? You get 2x equals to 2. And if you divide both sides, you get x equals to 1. Is that the answer to this?
No.
No. So this is wrong. You can't differentiate both sides because it's not an equality between two functions. In that case, derivatives do not lead to another equation. It doesn't hold. It's not true that if you differentiate both sides, it's still the same. However, if two sides are equal as functions, you can differentiate this side by using the chain rule. 2 comes down, x plus 1, and then the inside function is pulled out and you differentiate, but that's just 1. Differentiating this gives you 2x plus 2. And again, you indeed see that 2x plus 2 is 2x plus 2. So the two sides are still equal if you differentiate. That's why this still works. Okay, the two sides are equal as functions. Okay. Now, if you accept that's true, then how can we find A1?
Plug in 1.
No. You don't plug in 1, then these will survive, and you won't
No,
get.
A0 is 1.
Oh, okay. A1 is 1 you're saying. Okay. Yeah, that's right. Yeah. So you can plug in 0. X equal to 0 is what you want to plug in. And you get cosine 0, which is 1, equals to just A1. So you get 1 equals to A1. Now, how can we find A2 then?
Differentiate again.
Differentiate again, and then you plug in x equals to 0. And then how do you find A3? Differentiate and plug in 0. Differentiate, plug in 0. Yes?
But if you differentiate the second time, you get negative sine x, right?
Yeah.
And if you put it, is that negative sine is equal to 0?
Yeah, so you're going to get A2 as 0.
Okay.
All right, so I'll give you some time to try this. Find A2 and A3. Continue. So if you differentiate this, you get negative sine of x equals to A1 differentiates to 0, 2A2, x differentiates to 1, so you get 2A2. And then 2 comes down when you differentiate, so it's 6A3 x. If I write one more term, what would the next one be?
4A4.
4A4 x cubed, right? So when you differentiate that, it's going to be another 3 comes down. 3 times 4 would be 12A4 x squared.
Are you expecting us to do A4?
If you want to.
Huh.
Who did A4? Nobody? It's easy. Okay, you differentiate. Now what do you do? Once you differentiate, what do you do?
Plug in 0.
Plug in x equals to 0. You get negative sine of 0. By the way, sine of 0 is 0, so this will be just 0. Equals to 2A2, so that A2 must be 0. Okay. Then you differentiate again. Negative sine differentiates to?
Negative cosine.
Negative cosine. 2A2 differentiates to?
0.
0. This differentiates to?
6A3.
6A3 plus 12 times 2, that's 24.
24A4x.
A4x, and then plus da. And then you plug in 0 again. You get negative 1 equals to 6A3. That's just 0, so you get A3 as? Negative 1/6. Okay. Then if you differentiate again, you get sine. Sine of 0 is?
0.
0, so the next one must be?
0.
And we kind of see the pattern here. Every A even would be? 0. The A odd one will have alternating signs, right? It will be 1 and then minus 1/6. The next one will be positive. And then if you actually do A fifth, you'll see that A fifth is positive 1/120. Now, where would this number come from? Well, realize that 6 appeared because of 3 and 2. Where did 3 and 2 come from? It's from differentiating x cubed, right? When every time you differentiate, it comes down as 3 times 2 times 1. 3 times 2 times 1 is 6. So this one also is really 5 times 4 times 3 times 2 times 1. So it's really 1 over 5 factorial. So instead of actually writing down the explicit numbers, if you just write it in terms of factorials, you'll see that there's a pattern. The pattern is like this. Sine of x would equal to x minus 1 over 3 factorial. Instead of 6, I'm going to write 3 factorial, 3 times 2, x cubed. And then plus 1 over, next one's 5 factorial, x to the 5th, minus 1 over 7 factorial, x to the 7th. Guess what's the next one?
9.
Plus 1 over 9 factorial, x to the 9th, and so on and so on. Okay? Now, you should also know how to write this in sigma notation. It's a bit more involved, but to get odd numbers are 1 less than even numbers, right? So you say these numbers here, you write it as 1 over 2n minus 1 factorial. Then this is an odd number because 2n is an even number minus 1 would be an odd number, right? And since these two numbers match, the exponents should be the same thing.
But why do we have x?
Why do we have x?
Why do we start with x?
Oh, well, because we got a1 as 1.
Oh.
a1 is 1 and a0 is 0. So if it's like 1, that's like sine x equals to x, and then 0. Okay. All right. So you have this, and then the signs must alternate. How do you make signs alternate? You put
keep on going negative.
negative 1 to the nth power, or n plus 1. So n starts from 1 through infinity. And indeed, when you plug in 1, you get 2 times 1 minus 1. It gives you 1, which is the very first term, 1 times x to the first power. But then, if this is 1, it will be minus. So the sign is wrong. You should put plus 1 here. So it's a bit hard to write, but it's n plus 1 here. Then it's that. Okay. So that's the formal way to write it. Yeah, so that's called the MacLaurin series of sine. Now the fun part will be if you can actually verify that this is true. There are two ways. One would be actually to do the proof, which I don't think is going to be fun at all. Proofs are not fun, right? So let's just use computers to verify our results. So I have your screen here. Let me see. Okay.
Oh my God.
And the screen is Python, as you know, right? And some of you are taking Python classes, right? Here's how you draw graphs in Python. First, you want to use something called Pylab library. So I'm going to do from Pylab. Oh, let me make it bigger. Pylab, import everything. Sadly, the Pylab doesn't have the factorial library, so I'll have to make my own. I'll just define factorial of a number n as, let's see, so p is 1 for I in range of 1 through n plus 1. P times equals to I, and return p. Okay, so there's my factorial function. Okay, so now I'm going to do put the x coordinates. So I'm going to choose the x coordinates as linear space from negative pi to positive pi, and we'll divide it into 101 points. Do you also do MATLAB?
We're going
A
to start
little
with
bit.
this.
A little bit. Okay, so this is like a very common MATLAB command, but the Pylab allows you to use these MATLAB commands. Okay. So those who have done MATLAB will see that it's very similar. Okay, so I have that, and then let's plot the x comma sine of x. Here's the graph of sine of x. It's in blue. Now we're going to plot this against the x minus 1/6 of times x to what power?
The nth power.
To the third.
Third power, because 1/6 is the 8/3, right? 8/3 is negative 1/6. So you get this. So tell me what the orange is and what the blue is.
It's a cool logo.
Blue must, yeah?
Blue is the x sine x graph, and
Yeah, x comma sine x graph. In other words, sine x graph is the blue, and the orange is
the orange is the other graph. It's the x minus 1/6.
6x cubed, right? X minus 1/6 x cubed is what you have. And while they look very different, do you see that in the middle they're virtually identical? They're very similar, right? Now,
So
if we,
you add more to the end. of
yeah,
the
then
pulling
it's
of-
going to be better. So what's the next one? It's 1 over. What's the next one?
5 factorial.
5 factorial, which is 120, right? So 1 over 120 times x to what power? Fifth power, right? Ah, it's better now, right? It agrees more. Now, let's, I don't know the factorial of 7, so let's use this. Why is it taking so long? 5,040. Okay, so what I'm going to do is I'm going to now subtract 1 over 5,040 times x to the 7th power. Oh, now it's very close, right? Let's do one more. Factorial of 9. Whatever that is, we're going to put plus 1 divided by this gigantic number. Okay, and then times, times x to the 9th power. And then, wow, now it's like indistinguishable. Okay. So that's why we can believe that the Taylor series does exist. Of course, there's a proof, and if you actually go through the proof, you will accept it more. But I think this is a good enough proof for most of you who are engineers, right?